We are now going to talk about implicit differentiation. Up until now, we have learned how to take derivatives, and although it may not have been ever said, up until now, we have really done what can be called explicit differentiation. So for example, the kinds of functions or equations that we have been taking the derivative of usually look something like this. F of x equals x squared plus 2x. Or, oftentimes, we write it, instead of f of x, we replace it with y. Now, as I teach this, I'm going to mainly use y and not use function notation because it's a little easier to explain. If we were to take the derivative of this, like we've been learning the last few lessons, you notice you have x's over here, and just to do this problem, hopefully would seem very simple to you. You would say dy dx would equal 2x plus 2, so you take the derivative of x squared, right? 2 comes down front, subtract 1 from the exponent, and derivative of 2x is just 2. So that now hopefully is a very simple problem. But really there's a lot more going on in getting from here to here than we've talked about up until now. So let me take a step back and sort of approach this in a little bit different way, and that's going to become important because in a little bit we're going to want to take equations like this and we're going to be asked to find the derivative of x with respect, the derivative of y with respect to x. And from now on, I want to point out the language of what I say is very important, although you've heard it many times before. dy dx, once again, the way we sort of describe this is you're taking the derivative of y with respect to x. Now, if you look back up until now, every single problem that we've taken the derivative of, they've all been y equals, and then you have a bunch of x's on the right-hand side. And we learned a lot of derivative rules to figure out the derivative of all the x's. Well, look here, this is something different. We don't have y equals some function of x, we have y cubed equals x. So the question is, how do we take the derivative of this when the one side is not simply y, but we've got something else going on here? And really, implicit differentiation is really going to be all about, if we're given an equation with both x's and y's, how do we find the derivative of y with respect to x? Now that, it's almost like, let me actually write this phrase down because it's very important. dy dx really means the derivative of y with respect to x. So this with respect to variable is whatever the variable is sort of on the bottom of our little derivative notation here. And that's really the key. Let me show you why. Let me go back up here. When we took the derivative of this equation, do you know what we were really doing, though we didn't say it? To take the derivative of this equation, what we're really doing is we're taking the derivative of both sides of the equation. And by that I mean, a lot of times we like to write the derivative of both sides with respect to x you write like this. In the world of math, you can do anything you want to one side of the equation as long as you do the same thing to both sides. So I'm going to take the derivative of both sides. Now the key is, when you take a derivative, you have to look at the variable you are taking the derivative with respect to. In this case, we're taking the derivative with respect to x, because x is here on the bottom. Now here's the key. On the right-hand side, whenever I'm taking the derivative with respect to x and my variables are simply x's, I just apply the derivative rules that we learned. So for instance, the derivative of x squared would be 2x. Derivative of 2x with respect to x is just 2. Let me finish this problem in a minute, but let me just now try and stress a point. And the whole point is the idea about what you're taking the derivative with respect to. So for instance, say I want to take the derivative of x cubed with respect to x. Now since the variable I'm looking at and the variable I'm taking the derivative with respect to, since they're the same, I just apply all the derivative rules we've just learned. So this one, the 3 comes down, you subtract, and it's 3x squared. Once again, to do the expression I just did, the derivative of x squared plus 2x with respect to x. The first term, it's an x. Derivative with respect to x, 2x. Second term, 2x. Derivative with respect to x. But now, what would happen if I now took the derivative of y cubed with respect to x? So now notice the derivative, the expression I want to take the derivative of, that variable is different than the variable I'm taking the derivative with respect to, right? This is with respect to x, but you notice my expression or my function has a y. So in that case, what do we do? Well, it's not hard, because what you do is you go ahead and take the derivative of y cubed using our normal derivative rules, right? So it's just 3y squared. Matter of fact, I'll call this part, all we did was take sort of like the normal derivative. But if the variable in your expression is not the same as the variable you're taking the derivative with respect to, in other words, up here, x cubed and x, you just take the normal derivative rule and you're done. But here, it's y cubed and x, since these are different, you go ahead and you do the normal derivative rule, but then at the end you always have to multiply whatever your new variable is over dx. Since I have y's in my expression here, I take the normal derivative of y cubed, but then because this y is different than the x down here, I have to, at the end, just always multiply by dy dx. If I look at this one, instead of x squared plus 2x, if those became y's, in other words, say I'm given this expression, and I want to take the derivative with respect to x, I can do that. However, since my variable up here is a y and down here is an x, I go ahead, so the y squared is 2y, but then I have to multiply by dy dx because these variables are different. And then the derivative of 2y, if I take the derivative of 2y, it's just 2, but because my variable is y, and then I have to multiply by dy dx. So the rule is, or the key is, look at the variable or the variables in your expression or your equation, and then you have to compare it to what you're taking the derivative with respect to. What if I go back to y cubed, and I would like to take the derivative of y cubed with respect to y? All right, here's the variable in my expression, or my function. Here's the variable I'm taking the derivative with respect to. Since they're the same, you just apply the normal derivative rule. There's nothing else. It's only if it's different. What if I have x cubed and I decide to take the derivative with respect to y? So I've got an x up here and a y down here, so I apply the normal derivative rules to x cubed to get 3x squared, but because these variables are different, I then have to multiply by dx dy. So that's sort of the rule. So now that we sort of understand that, let's go way back to this original equation. Normally what they do, they'll give you an equation and they'll say, what does dy dx equal? And we call dy dx the derivative. So they say, here's an equation, go find the derivative, which means dy dx equals what? The way you take the derivative or find the derivative when you have an equation is you take the derivative of both sides. Now in this case, it's with respect to x. So if I take the derivative of both sides with respect to x, now let's go to the left-hand side. You notice my variable is y, but the variable on the bottom with respect to is x. They're not the same. So I go ahead and take the derivative of y with my normal derivative rules. Derivative of y is just 1. But because these variables are different, I have to multiply by dy dx. I have to go to the right-hand side. If I take the derivative of x squared, notice x squared, x, and x are the same. So I can just apply the normal derivative rule and get 2x. And then derivative of 2x, once again, the variable here and the variable in the bottom is the same. And that's why you end up with this result, which you knew how to do from the beginning. So based upon that information now, let's start doing a few equations that can start to get a little trickier. And actually, as we do a bunch of these problems, really, I think we can basically summarize how to do this kind of thing in 2 steps. So here, how to find a derivative step 1, take the derivative of both sides of the equation. And let me just put this reminder, beware of the variables. If the variables are the same or the variables are different. Remember, if they're different, after you take the normal derivative, you have to multiply by that extra dy dx term or whatever. So once you take the derivative of both sides, then you oftentimes have to do a little algebra and solve for the derivative. All right, so let's just do a bunch of examples, and hopefully you'll see that this isn't real difficult. How about if we were given this equation, three x cubed minus y squared equals 8. So here's an equation with both x and y. We want to determine what the derivative is with respect to x of y. So I'm simply going to take the derivative of both sides with respect to x. And I start applying my derivative rules, but I have to be aware of the variables to know what I have to do. So this first one is the derivative of 3x cubed with respect to x. The variables are the same. I just apply my normal derivative rules and I'm done. However, the second term, I'm taking the derivative of y squared with respect to x. Since the variables are different, I go ahead and just apply my variable rules to y squared, which would be 2y. But because the variables are different, I then have to multiply by dy dx. On the right-hand side, when you take the derivative of a constant, it's 0. So now I've taken the derivative of both sides, and the ultimate goal of this problem was to solve or to see what dy dx equals. Well, I have a dy dx equation now, so to solve for it, I need to get the dy dx by itself. So now it becomes an algebra problem. We'll subtract 9x squared from both sides. And if I want to get dy dx by itself, I'll then divide both sides by negative 2y. And the negatives cancel out. And that should be your derivative. All right. Now, just to make sure you understand this, let me go ahead and occasionally change some of the variables so you don't get into a rut of always thinking everything has to be x and y, because in the real world, not everything is x and y. For instance, this one is y squared plus t squared equals 1. And what they want to know is the derivative of y with respect to x, or with respect to t. It's not x, it's t now. Well, it's the two steps, right? Take derivative of both sides with respect to t. On the left-hand side, let's go see what happens when I take the derivative of y squared. Well, I'm taking the derivative of y squared, but the variable I'm taking the derivative with respect to is t. Since those are not the same, I'm going to take the normal derivative of 2 of y squared, which is 2y, but then I have to multiply by dy dt. And now the derivative of t squared, Now you notice the variables are the same. Derivative of t squared with respect to t. So I just take the derivative, and I'm done. And the derivative on the right-hand side, derivative of a number is always 0. So now I want to solve this for dy dt. So let's subtract 2t from both sides. If I divide both sides by 2y, and there's the derivative. All right, hopefully that was not too difficult. All right, let's do a few more. Now you notice the next couple problems I'm going to do, we're doing the same method, but what is becoming a little more complicated is the initial equation. And when you take the derivative, there's some more work involved. In other words, looks like a pretty simple equation. X cubed times y squared equals -5. And we want to know the derivative dy dx, derivative of y with respect to x. Well, going to take the derivative of both sides with respect to x. Now the right-hand side is pretty straightforward, right? Derivative of a constant is just 0. Left-hand side, now we have x cubed times y squared. Two different variables, and they're actually multiplied. So what rule did we learn when you're trying to take the derivative and when you have two factors multiplied together? What did we learn to do? We have to use the product rule. So I'm going to go ahead and I'm going to write this out explicitly just so it's clear what's going on so you don't get confused. For me, product rule, I'm going to write the first factor, and then here I'm going to take the derivative. I'm not going to do it yet. I'm just going to write it out. So the first factor times derivative of the second factor plus the second factor times the derivative of the first factor. So this is the product rule. That's simply taking the derivative of x cubed y squared. So that whole thing equals 0. So let's take the derivative. X cubed, derivative of y squared with respect to x. Variables are not the same, so you go ahead and take the derivative. And then you have to multiply by dy dx. For the second term, you have derivative of x cubed with respect to x. Now there's a case where the variables are the same, so we can just simply apply our derivative rules and get 3x squared, and there's nothing else in that term. All right, so now we've taken the derivative of both sides of this equation. Now the ultimate goal is to solve for dy dx. So it looks like I need to subtract this term here. So let me write out 2x cubed y times dy dx equals -3x squared y squared. And now if I want to solve for dy dx, I just divide both sides by 2x cubed y. And of course, if you want to, and you probably should, you should cancel some things out of the top and the bottom. In other words, I think I'm left with y over x. If I didn't mess up in my head. X squared over x cubed leaves an x in the bottom, y squared over y leaves a y in the top. That should be dy dx. Now, just for fun, let's do a problem and not use x and y. Matter of fact, let's use x times t minus x plus 2t equals 3. And I want to take the derivative of x with respect to t. So normally, we typically like to use variables x and y, but you can use all the different variables. So here we just decided for fun, instead of y, we'll throw in some t's. We want to find dx dt. So I'm going to take the derivative of both sides of this equation with respect to t. Now I notice right away I have three terms here. This first term, I have the variable x times the variable t. So like I have two functions multiplied together. I'm going to have to apply the product rule. So I'll write the first times the derivative of the second. The derivative of t with respect to t is just 1. Now to finish the product rule, now I'm going to write the t and take the derivative of x with respect to t. Well, the derivative part of x is just 1, but then you do have to include the dx dt, since the top and bottom variables are different. So this all comes from there. So then the derivative, subtract derivative of x with respect to t, derivative of the x is just 1, and then you have the dx dt. Now here, derivative of 2t, 2, and since t is the same variable as the variable I'm taking the derivative with respect to, you just take derivative of t and we're done. Now the right hand side is going to be 0. So if I sort of make this a little prettier, this is like xt times dx dt. Oops, that's not correct. It's just x plus t times dx dt minus dx dt plus 2 equals 0. Now if I'm going to solve this for dx dt, let's move the x and the 2 to the other side. I'm also going to factor out dx dt, so I'm going to do 2 steps here. So derivative, factor out, times t minus 1 equals, wow, I keep making mistakes, sorry, negative 2 minus x. So then to finish this off, if I want to solve for dx dt, I simply divide both sides by t minus 1. And actually, to be honest, they don't like all those negative signs. I multiply top and bottom by negative 1. This is a more normal way to write it. Derivative of x with respect to t is x plus 2 over 1 minus t. All right, so I hope you're getting the hang of this. Once you see a few of these done, not too difficult. Let's do one last problem, and this one's sort of messy, but I want to just show that when you do these problems, you're just applying mainly the derivative rules you've already learned. So just to keep things interesting, I'm going to have an equation with the variable p and the variable x. P squared over p minus x equals 1. And in this case, we want the derivative of p with respect to x. So do what I always do. Take derivative of both sides with respect to x, since that's what I'm looking for here. Right-hand side is pretty straightforward. Derivative of a constant is 0. Left-hand side, I need to look at. So I'm taking derivative of this. I got the variable p, the variable x. But you notice I got a fraction here. What do we do when we want to take the derivative of a fraction? Yeah, we have to use the quotient rule. So let's go back over. The quotient rule says the low times the derivative of the high. So I'm going to take the derivative of p squared with respect to x. So you do 2p, so bring the 2 down, subtract 1, but then you have to also multiply by dp dx. Quotient rule says low times derivative of the top, and then the top times the derivative of the low. So what's the derivative of p minus x? Derivative of p with respect to x is just 1, but then you have to put in the dp dx. So once again, I'm looking at the derivative of p minus x. Now the derivative of x with respect to x is just negative 1. So to review and make sure I made a mistake, trying to apply the quotient rule. The low times the derivative of the top minus the top times the derivative of the low all over the low squared equals 0. Now, I ultimately wanted to solve for dp dx. This looks pretty messy, and that usually is what happens. Whenever you have to use a quotient rule, things can get messy very quickly. Let's see what we can do here. First of all, the right-hand side is 0. If I want to get rid of this fraction, I would multiply both sides by p minus x squared, and it just goes away. So really, if I rewrite this, this is really the equation I have. And I'm going to go and multiply out these parentheses just to save a step. What I'm going to do is I'm going to factor out this dp dx. In the first term I get 2p times p minus x. Then if I factor out the dp dx here, and while I'm at it, let's go ahead and I'll just subtract that from both sides. Now, if I would get dp dx by itself, divide both sides by this big bracket. As I write this, I'm going to go and multiply out this parenthesis here. So it's 2p squared minus 2px minus p squared. And then it does look like a couple things can happen. First of all, 2p squared minus p squared is just p squared. So you have negative p squared over p squared minus 2px. I notice I have a p in all three of these terms. So I'm going to divide out the p, and I'm going to switch these around to switch the signs. Hopefully you know what I'm doing, so... I switched some... let me do this over here to the side. Some of you might be wondering, how did he get that? So here's what I had. First thing, I want to cancel a p out of all three of these. And then if I can get rid of negative signs, if I multiply top and bottom by negative, you can end up with this. All right, so that was a messy problem. And that's what normally happens when you have to use a quotient rule. So hopefully now, implicit differentiation, not that difficult. The key is, what you're going to do is you can take the derivative of both sides with respect to a certain variable. And then as you go take the derivatives of everything, you have to keep in mind what your variable is. And if it's the same, you just apply the normal derivative rules. If the two variables are not the same, then you have to, at the end, multiply by that final dy dx or dx dt or whatever. All right, so next lecture we're going to talk about related rates, which is just really more implicit differentiation.